Hello everyone. In this lecture, we are going to talk about one-dimensional line defect. The one-dimensional line defects are dislocations. They are lines through the crystal along which crystallographic registry is lost. They can control yield strength and plastic deformation and also participate in the growth of crystals and in the structures of interfaces. The one type of dislocation is edge dislocation. Firstly, let's make planar cut as shown here, and then apply a force the body above the cut that tends to displace. And you can find displacement of the two lips of the cut in the right side figure, and you can also find the edge dislocation which can be formed within slip plane. Let's think about the edge dislocation in a simple cubic crystal structure. In this scheme, the B is a lattice vector, which is called as the Burgers vector. It should perpendicular to the dislocation line. And this like dislocation can be created by making a cut on the dashed plane as shown in this scheme. And they allow the atoms to rebound across the slip plane. So Burgers vector B is given by A100, and A is a vector along the edge of the cubic unit cell. And we can find also one extra vertical half plane of atoms above the slip plane. And for the Burgers circuit, let's choose a direction for the dislocation line and draw a clockwise closed circuit in the perfect crystal, the 100 plane. But in the presence of dislocation, we fail to close this circuit. So the vector required to complete the circuit is Burgers vector B. And motion of edge dislocation. So as you know, dislocations can control the plastic deformation of crystalline solid. So they can glide. The bond must be broken for each phase as shown here. And they can also climb. The movement up out of the plane makes elimination of atoms by vacancy, and movement down makes addition of atoms as shown here. The different type of dislocations is screw dislocation. Let's slice the solid pathway through in the direction of its width as shown here, and displace it by a vector B, Burgers vector, that lies parallel to the dislocation line, and re-weld it so that it is continuous across the plane of slip. And you can find residual distortion which concentrates at the dislocation line, and you can also find isolated linear defect. It is screw dislocation. Dislocation in real materials should have mixed dislocation of edge dislocation and screw dislocation. In mixed dislocation, Burgers vector B lies at an intermediate angle, and they interact with other elements of the microstructure. So dislocation lines are normally curved. And dislocation can be considered as a boundary of surface over which the crystals has slips. And you can find in real material this like dislocation loop, a boundary of surface on which slip has occurred and can be created by a process that is equivalent to a slip of cylinder of material above the loop by a vector B as shown here. We can find three important properties of dislocations. The first, they bound surfaces that divide the crystals. So the part above the surface is slipped by the Burgers vector B. The second, the slip on the surface bounded by the dislocation. So it is constant and equal to a lattice vector. And Burgers vector B is a lattice vector and same value at every point on dislocation line. The third, the slip is constant. So a dislocation cannot simply end within a material. There is always a boundary between a slipped and unslipped area. And then let's think about one important example for the formation of dislocation array at grain boundaries. So we can use this like the model materials, the antimony telluride and telluride mixture phase. So if we use the lead arrowed the composition and by using melt spinning technique, the melt spinning is one of the important rapid solidification process. So we can fabricate this like nanoscale heterostructures of antimony telluride and mixture phase of tellurium and eutectic phase. And in order to clarify the formation mechanism of dislocation array, we need 4 different samples. The first is the as prepared melt spun ribbon, and the second sample is heated green pellet with solid state antimony telluride and liquid state tellurium, rich phase. And the third, compacted pellet at the intermediate state, and final sample is compacted pellet at the final stage. In the first stage sample, so as prepared melt spun ribbon, you can find this like free aligned grain structure from the crystal orientation mapping. And this triggers rapid grain rearrangement during the sintering process. And also you can find a very interesting feature in these TM images, the tellurium homo interface between excess tellurium and antimony telluride crystals, because the interface is terminated with tellurium layer. And in the second stage sample, the heated green pellet, you can also find the this like tellurium homo interfaces can maintained even at higher temperatures. This is related with the grain rearrangement during the sintering process. And at the compacted pellet, in intermediate state, you can find that the excess tellurium is liquefied and expelled out from the boundary, and you can also find more pattern as a trace of misfit dislocation arrays. This means that the simultaneous grain rearrangement and dislocation formation. And in the final sample, you can clearly find that the dislocation array with periodic spacing, the defining low angle grain boundaries. And in geometric phase analysis, you can find the periodic distribution of misfit dislocation cores and strain field around the dislocation core. So in this like model study, we can find 3 important prerequisites to make the high density dislocation array at grain boundaries. The first, eutectic system between target material and its constituent element. And the second, the plate type grains of the target material accompanied by eutectic phase at lower melting point. And the third, solid state homo interface between the target material and eutectic phase. So in this lecture, we talked about the one-dimensional line defect dislocation, and also discussed about how can we generate this like the one-dimensional defect structure by material and processing engineering. Thank you.